So with our journey with Hess, we've seen that any path from the reactants to the products will be the same enthalpy difference no matter where the path goes, okay? And then we saw that the heat of formation values, okay, gave us a nice definite path that a lot of scientists use, and we can look up the enthalpy values in a table, okay? Another one that we can use is this one here, which is the heat of atomization, and it couples in with the heat of formation as well, okay? So heat of atomization is the energy needed to atomize an element from its natural standard state, so how it exists as an element by itself, well, as a singular element at 100 kilopascals and 25 degrees Celsius, or it's at that point that we call the heat of formation. And what we're going to is singular gaseous atoms, or we're breaking all the bonds and all inter and intramolecular forces, okay? So we completely separated each atom in there. So that's the heat of atomization, okay? It's going from where we got the energy to with the heat of formation, which is in elements by themselves at the standard temperature and pressure, and we're going all the way to singular gaseous atoms, okay? So for example, the heat of atomization of chlorine, Cl2, is the energy needed to take half a mole of chlorine gas, how it's found in its natural state, and turn it into 1 mole of singular gaseous chlorine atoms. And this energy we can look up for a table is 122 kilojoules per mole, okay? So we've got an element in its natural state, and we're heat of atomization is the energy needed to go to gaseous single atoms. From my example, if we want singular gaseous chlorine, we need half a mole of chlorine gas, which is how chlorine is found at 100 kilopascals and 25 degrees Celsius. So the energy needed is 122 kilojoules per mole, okay? Now, this heat of atomization is really handy because it fills in this missing extra energy from where you end up with the heat of formation to a final state of completely separated atoms. Okay, so it couples with the heat of formation, so you can take any reactants and go to the elements in their natural state and then jump up to individual gaseous atoms. So you're going from reactants to individual gaseous atoms, okay? And it's the negative heat of formation to go from there and there, and then it's the heat of atomization to go to there, okay? So here's just a little tip and a table from the textbook. Okay, heat of atomization equations and values always result in a singular gaseous atom. Okay, so this is a little tip. So here in my example that I used earlier, you saw that chlorine found as Cl2 at standard temperature and pressure. We wrote it as half a mole of Cl2, so we got the stoichiometric 1 mole of chlorine singular atoms gases, okay? And that is the heat of atomization value for chlorine, 122 kilojoules per mole. Okay, so for zinc, to get it as 1 mole of zinc gas, well, we just start as one mole of zinc solid, and that's the heat of atomization of 131 for zinc, okay? So make sure with these heat of atomizations that you're using stoichiometry so that you've just got the product there as a singular stoichiometry of 1. So here's a table from the textbook that's just got the heat of atomization of different elements, okay? And we can use that in our questions. Determine the amount of energy required to separate gaseous SO3 into individual gases, given the heat of formation of SO3, the heat of atomization of O, and the heat of atomization of sulfur, okay? So we're starting down here as SO3 gas, okay? And then we're going up to some energy point where we've got the elements in their natural state. So sulfur in its natural state is sulfur and oxygen, O2. Okay, and then we've got sulfur plus 3 times oxygen. Okay, have I done this right? Let's see. Okay, so the amount of energy required to separate gases into... I think I'm good. Okay, so this is... I want the negative heat of formation. So that equals 396 kilojoules per mole. To go to there. Okay, and then I want to go from there to there, so I need 1 times the, 1 times the, pen, heat of atomization of sulfur. I know I've got O2 there, but it's, well, should I say that it's 3 halves of O2? That's better. Okay, plus 3 times the heat of atomization of oxygen. Okay, is 249. Or I'm not writing the values yet. Heat of atomization of oxygen. So that equals sulfur 279 plus 3 times 249. So E total equals 396 plus 279 plus 3 times 249 kilojoules per mole. Calculator for the last step. 396 plus 279 plus 3 times 249 equals 1,422 kilojoules per mole. So it takes 1,422 kilojoules per mole to separate gaseous SO3 into individual gaseous atoms. Okay, gonna leave it there and I'll start talking about bond energies.